For me, pi1 will be the fundamental group scheme defined by Nori. I will give some details on the fundamental group scheme, but before I recall the aim of this job is to generalize this result in the language of fundamental group scheme. For the fundamental group scheme. So I will give some very brief details on the fundamental group scheme. It was defined by Nori in 76, and then in 82, he first defined the fundamental group scheme of a scheme over a field K as the group scheme naturally associated to the neutral Tanakian category of essentially finite vector bundle over a scheme X. We don't use the Tanaka approach today, so I don't give more details on that. But some years later, he gave a more general and intuitive definition that has been generalized by Gasbarri in 2003 for schemes of a Dedekind scheme. So that's the.
What do you mean exactly by pi1 et al. Abelian?
Abelian is the fundamental group parameterizing all abelian covering over X. We know that from this morphism, we know that every abelian covering over JC go to an abelian covering just pulling back over C, and we are asking if an abelian covering over C comes from JC.
I guess the question is K separably closed or not?
Yes.
Sorry?
Is K separably closed or not?
I think that the first proof has been done for K separably closed, but I think it works for every K. This is probably done by Serre.
You mean geometrically abelian? pi1 et al. Geometrically abelian. Because pi1 et al. Of G may not be abelian in itself if K is arbitrary.
If you put ab on the left side, you definitely have to put ab on the right side.
For example.
It's not. I think you mean geometrically
right side,
abelian.
then what is on the right side in general is not abelian, therefore it can't be an abelian.
Okay.
Because you have extensions, we have eta covers which can be
Put up on both sides, is it okay?
But it's okay. I think geometrically abelian is okay.
Okay, we can say geometrically abelian. I will look at it.
If you put up on both sides, is it okay?
I don't know. Even that, yeah. Even if you put ab on both sides,
Because I know for the fundamental group scheme we don't need to put an ab here because Nori proved that it is always abelian. So probably because of that I thought it was always true. So thank you.
take an abelian curve variety over an elliptic curve over finite field.
Mm-hmm.
Pi1 et al. Of this is not abelian because there is Galois action on the points of the elliptic curve.
oh,
Let's suppose that little k is algebraically, is finite field. And your x is really an elliptic curve. Then pi 1 et al. Is definitely not pi 1.
Well, I forgot how it goes, but maybe the fundamental group scheme is something different, right? It's like a sheaf
Yes.
over
So,
FK or something of this sort. So there is abelian relationship. I think it's something like this. We'll see.
Yes. Okay.
yes,
So maybe.
so I will be more precise on that. Probably you say everything works well if the k is separably closed.
Yes.
That's I can do this assumption. Okay. Sorry for not be precise in that. I will define the fundamental group briefly. So consider the category. Take a scheme over a Dedekind scheme. So S is a Dedekind scheme. S is a Dedekind scheme. X is a reduced and reducible scheme. Reducible is needed if S is not a field. If S is a field, we can ask connected, but we can use this assumption for the moment. And F is faithfully fed. Moreover, we need a section of F, and what Nori and Gaspari prove is that if you take the category of finite torsor point over x pointed over small x, it is filtered. So take the category Px where the objects are triples. Where Gi is a finite and flat group scheme. Yi over x is a G torsor, Gi torsor, sending Yi on small x. And the morphism, I just say what morphisms are morphisms between triples commuting with the action of the group schemes. So Nori and Gaspari proves that this category is filtered. What does this imply? That we can define the projective limit of the Gi, and this is the fundamental group scheme of x in small x. What else? I can think it's all for the details on fundamental group scheme. Just to have an idea of what it is if you didn't know before today, just take S the spectrum of an algebraically closed field of characteristic 0. So every torsor, every group scheme finite and flat is étal and constant. So it is anything new because it is just a group scheme associated to the étal group scheme of X. What else? So now I give a last definition that I will use strongly in what follows.
Sorry, I'm a little bit confused. What does the category PF have to do with the group?
The category, because the morphisms between the group schemes are the morphisms occurring in torsors. And of course you can define you define I only say that you can define a group scheme, but you can define a universal object, which is a universal triple. So you have a universal torsor pointed, a universal pi1 torsor pointed in a point over X. And morphism, I can be more precise, are morphisms of X schemes commuting with the action of group. So maybe it is more clear. So
so part of the filter is that actually if you have some yi over x with the gi, and you have some yj over x, then that is dominated by something big X.
Yes, of course. Yeah, of course. The part of the proof is that you have two such triples over a third one. You have donc a fourth one that dominates the diagram.
The question was, and then is gi a quotient of dominating one? Is it just general nonsense, or you have to actually do something?
It is. But GI in general is not a quotient of GI can be can contain other torsors, and so for example, you can have a morphism which is not faithfully flat and not even schematically dominant, because in this category you have torsor that contains other torsors, for example. But of course, the more important are those for whom this arrow is schematically dominant. That is, by the inverse arrow on algebras is injective. So, for example, you can have this situation where here you have a GJ torsor, which where GJ contains JE and YJ contains YI. So in general, we consider every torsor.
So that this pi, this pi1 is actually not a pro group scheme. It's just a pro object.
No.
It's
It
pro-group scheme.
is a group
It's
scheme.
projective limit.
It is a group scheme.
Project is the pro, I understand that actually it's not a projective limit.
Yes, it is a
Why do you
projective
think it
limit.
I think it's
It is a projective limit of every torsor occurring in this category, and by I think that the only assumption that we need for a pro object to be an object is that the morphisms are affine, I think, and this is the case.
of co-financing. So dominant, and so the GIs are quotient.
Yeah, also, I think somehow you need to write that limit in a more careful way. If you just write limit over I,
Yes, it's probably.
so limit over the category or something, right?
This is the limit of the category.
Yes, it's an ugly writings.
But the limit makes independent sense. Forget about any access.
Well, exactly.
And you can take the trivial torsor for each GI if you want. Then you get
No. Yes, I can say the limit in the category.
Yeah.
We can say like that. Okay, but it's just a usual way of writing that I incorrectly used. But
Also, this way of writing, so, okay, yeah, I guess this is okay. So, I guess it's equivalent to the following, right? Consider the universal torsor for a finite flat group S group scheme, for universal pro-torsor for finite flat S group scheme over X, right? And take the group scheme theoretic fiber over X or something.
the scheme theoretic fiber.
Fiber over X of the universal torsor. That
Okay.
might be what they said, right?
Yes, it is. Yes, of course. Yes, it is. Simply because I think every torsor on the fiber is its group scheme acting on it. So the limit of yi over small x is actually the fundamental group scheme. So if you want, I can go on. Sorry. So I use the same notation in the morphism of this category, where GI are commutative. This can always be defined, and now I can pass to the second point. I will state the main results, but before I need some additional assumptions, which would seem very strong, but in many relevant cases that I will describe, this is always true. So, for example, the notations are as before, so F is a morphism from X to S. We, as this morphism holds universally, this isomorphism holds universally. That is, it commutes on base changes. Then I always ask the strong condition that the Picard scheme that I write like this, Picard scheme exists. I don't say almost anything on the Picard scheme, but thanks to this assumption, if it exists, it represents the relative Picard factor, so represents. So I don't define the Picard scheme, but in the case that I'm interested in, so if we take an S scheme, this is just the Picard group of x times t quotiented or a critical group of t. So we have, in this case, if it exists, we have a nice description. We ask more than this. We ask that the x0 and x tau exist as closed and open subschemes of peak x's. I will define orally x0 and peak tau exist as closed and open subgroup schemes of S. I ask even more because it is not enough. I ask x0. Probably before continuing, I just say something on these two group schemes if they exist. So if S is a field, x0 is just the connected component of peak x containing the unity. And if S is any scheme, it holds for every scheme. Here S is a Dedekind scheme, so we can assume as the S is Dedekind scheme. But for this discussion, we don't really need it. So in general, if S is any scheme, it is a scheme that on the fibers is the nuclear component of the peak x on the fiber, which doesn't imply that this is the connected component of the peak scheme. But we want this assumption, because we want x0 to be in some important case an abelian scheme. That's why we construct it like this. So this is assumption 4 is a projective abelian scheme. And what else? Yes, peak tau to be flat and projective over S. So what is peak tau? Peak tau, I will write describe it. Take the multiplication by n map from peak to peak and consider as a set the union of the reciprocal image of n of the peak 0. This is by definition peak tau. And we ask it is a scheme flat and projective over S. So if all these assumptions hold.
Sorry, could I stop you just for a second? I just want to go back to the definition again, just for a second. So I think in this category, you're taking yi to be connected torsors, is that right?
No, I don't think so. You can take every torsor and but it is true that almost true that at least for over a field, every torsor is dominated by I say a strongly connected torsor. What I mean by strongly connected, a torsor it is a LNNO definition. It is strongly connected. I say HYI if its H0 is isomorphic to K. So it is in particular connected. But as I so over a field, these are the most important torsors because every torsor can be dominated by this kind of torsor. But
Well, how can a disconnected torsor be dominated by something like that?
sorry?
How can a disconnected torsor be dominated by something like that? I don't see that.
Because you have to a torsor, you can associate canonically after this.
Oh, by dominated, you don't mean that there's a dominant map. You mean just that there's a torsor mapping to it.
Yes.
Okay, yeah. In this category, there's a strongly connected torsor that maps to your torsor.
Yes, and I cannot say anything at the moment for a dedicated scheme, but all we can say is that you just can consider torsors where these morphisms are schematically dominant because you can factor, as you said, you can factor every morphism in a schematically dominant morphism and a closed dimension. But I don't know anything on the properties of these torsors, which are the most important. We can only consider those torsors, but the definition includes every torsor.
Yeah, I guess it's okay, but I keep getting worried about if we allow all the trivial torsors.
Yes, you have also trivial torsors.
But I guess
Why not? And these are torsors that factors through one. These morphisms factors through one, the trivial group.
Yeah, I guess when you take this inverse limit, pi1 doesn't surject onto any of it. Doesn't have to surject onto a given GI, right? So that's the point. Yeah.
Pro-connect.
Yeah.
Everything is dominated.
So if all these assumptions are true, and then I will describe some examples to have here, we can define the quotient of peak tau by peak 0. The assumptions are good enough to prove that it is a group scheme. And we can say more, it is a group scheme over S. It is finite. And smooth. So, for example, for trivial examples, if you take X an abelian scheme or a curve with integral geometric fibers, peak 0 and peak tau coincide, so this group is trivial. And so, and then, moreover,
So here you're initially taking the quotient in the FPPF topology or something.
yes, you take the quotient in the FPQC topology, but as I said, with these assumptions, one can prove it is representable by a group scheme, which is finite and smooth. This requires a little work to prove that. And moreover, we have an exact sequence. So I took XS. I will describe all the objects. We have an exact sequence where here this symbol means the Cartier dual. Here we have what we have already defined, the abelian fundamental group scheme of X. And here we have the fundamental group scheme or the Albanese scheme of X over S. Why I didn't define it? Because if these assumptions are satisfied, we can always define it. And what it is just the dual abelian scheme of X0, which is a projective abelian scheme. So everything works as it does. So the dual abelian scheme, which means X0 or X0 over S. And this morphism phi is no. So phi is the morphism used by the canonical morphism going from X to the Albanese scheme of X, sending the section into 0. As a corollary, if X is a curve with a smooth curve with integral geometrical fibers, then phi is actually an isomorphism. Why is this true? Because as I recalled you before, peak 0 and so on the side. So proved. We have what I stated at the beginning. I now state the second theorem. If I have time, I will give proof of theorem 1 and 2 for curves, because it's more simple, as you can imagine. So theorem 2 is the following. Take S connected and theta is generic point. So you can consider this situation, X over S, you can take its generic fiber. So every commutative torsor over x eta comes from a torsor over x. My torsors are always pointed, so pointed over x to x eta. Is the fiber of a finite commutative torsor over x pointed over small x. So here it is probably not necessary, but I add the assumption that it is quotient. What do I mean by quotient? I take this torsor that I call y, and G is the group acting on it. I mean by quotient that the morphism, the canonical morphism associated to this torsor from the fundamental group scheme to G is faithfully flat, which is equivalent in this case by saying that it's symmetrically dominant. Why is this true? I can take a sketch of this proof. I think in the case of curve, it's very, very intuitive. Proof for curves, plus assumption. So curves with smooth curves with integral geometric fibers. So we have seen that if we have a curve.
Oh, sorry. Sorry to interrupt. But what did you say over there? What every quotient commutative?
Quotient. I mean by quotient. If you take a torsor, it is pointed x, so it is a triple in the category that I use to construct the fundamental group scheme. So you have a natural morphism from pi 1 to G, and you ask these morphisms to be faithfully flat. You are over a field, so it's quite easy to prove that it is schematically dominant. So on the algebras, you have an injection.
So if this were a connected torsor, would this be a quotient commutative?
Sorry?
If y is connected, then is that sufficient?
In characteristic 0, yes. I think in characteristic P is not sufficient. You have to ask it is strongly connected.
In the previous sense. Then it's enough.
Yes.
Okay, I see.
So for curves, it's quite interesting. Because you take your torsor over x eta. This comes from a torsor over j eta because of theorem. I will say why. This comes from a torsor from over G because it is a special case. These are abelian schemes. I will briefly explain why. For the moment we trust, and then you take the pullback over X and you obtain so a morphism whose fiber is isomorphic to to the starting one. So we only need to prove that a torsor of an abelian scheme, an abelian variety, comes from a torsor of an abelian scheme who is it's a narrow model. But this comes from a result of Nori again. I think he proved it in '83. He proved that the fundamental group scheme of an abelian variety in the origin is the projective limit of the ng eta, where the ng eta are the kernel of the n multiplication by n. So we can say in some sense that these are the only torsors which are important for abelian schemes. It's true for every abelian variety, sorry, but here it's J eta.
So I just want to understand the structure of the torsor. So the point is, you start in this example, the theorem 2. You start with something x over s in such a way that peak of x over s satisfies all these properties 1, 2, 3, 4, 5. And then the assertion is, if you take a torsor over the generic fiber, which is quotient commutative, then it extends. Is that true?
Yes.
But you make already the assumption on peak of the relative.
Yes, the assumptions 1 to 5
are always
satisfied.
Okay, suppose under the assumption 1 to 5, you have the following. Okay.
Yes, of course. Sorry to not recall. Only in a moment I will give examples where these assumptions are always satisfied.
And what did you write there next to the proof?
Sorry?
What's in the proof?
These are a proof holding for curves.
Plus what?
Because we have an isomorphism of its abelian fundamental group with the fundamental group over J eta. So every torsor over X eta comes from a torsor. It is the pullback of a torsor over J eta. The theorem holds always.
Yeah, but I mean, but this is a smooth curve or something, or just any curve?
And yes, I haven't repeated, but the assumptions are always the same. That plus hypothesis, I mean the hypothesis of the previous property. So it is smooth.
Oh, it is smooth. Okay.
Smooth over S, and with
Right, then it's okay.
integral geometric fiber.
So that's stronger than hypothesis 1 through 5.
This implies hypothesis 1 to 5. So in this case, these results tells us that every torsor over J eta, at least every quotient torsor over J eta, comes from a torsor over J, and because essentially every torsor is dominated by multiplication map, I just give you a details. If you consider a torsor as a morphism from pi 1 to G, take a quotient torsor, it is dominated by that. This is equivalent as saying that every torsor is dominated by the multiplication by n. So this can be extended by nj. So now it's For example, you take the kernel of rho, you take the flat closure of rho in Nj, and then you take the quotient, which always exists, because it is a quotient of finite group schemes where it is flat. So you take the quotient, and this extends the morphism rho. So associated to this morphism, you have a torsor which extends the starting torsor. Why? Because you have an arrow from phi 1 x to nj, then an arrow to nj quotiented by this flat group scheme over S, and by properties of quotient, it commutes by Bayes changing. So we have a torsor that extends y prime. So I recall, you start from a torsor here. By the theorem, in the case of curves, this comes from this is the pullback of a torsor over j eta. You know how to extend this one over j, then you take the pullback, and you are done.
S here is any base, any connected base?
No, and everywhere S is a dedicated scheme.
Oh, it's a dedicated scheme. Okay, I get it. So then I guess the content of this must be the fact that the kernel of multiplication by n is a finite flat group scheme.
Yes, of course. Yes, at the moment I need to take dedicated schemes because fundamental group scheme is defined only over dedicated schemes. And why? Because in the proof there are arguments like that. You need to take the flat closure of something that. So
yeah. I mean, it was your assumption J is as nice as possible. So, so the kernel of multiplication maps are all going to be finite flat group schemes. That's the point, I guess.
Yes. Yeah. Okay. Yes. So for curves, it's quite clear. I don't prove the generality, but I just would like to describe examples where the assumptions 1 to 5 are always satisfied. Examples where 1 to 5 are satisfied. So the first example is the example of curves. We have already seen it, so I don't really argue. So the second example, is given by the characteristic 0. Characteristic 0, everything works well. So if you have a characteristic 0 and x over s is we need some assumption on this morphism is projective smooth. And we need the integral arithmetic either. And x connected. So this is sufficient to prove that we are in any dimension for x. In this case, every point is satisfied. But for example, since the geometric fibers are reduced, so point 1 is satisfied because since the geometric fibers are reduced, f star OX it's isomorphic to OS universally, and just what I just want to say one thing on this case. We need that in general we need for pick 0 to exist and be an abelian scheme. We need that the pick 0 of each fiber are smooth and of the dimension. That they are smooth, it's clear since we are in characteristic 0. And I think, but I theorem of the ring they are of equal dimension, so the problem for pick 0 doesn't exist. And for pick tau, it is moved simply because pick is moved. So yes, this is always the case when S is connected. So everything works well with characteristic 0. Now there are third interesting case. I put a question mark not because I don't trust NO, but because it's an example that I'm studying at the moment. So Renault in 78 proved that if you take S, the spectrum of R, where R is a complete discrete convolution ring of mixed characteristic such that the absolute valuation of is not greater than t minus 1. Then, what else if you take x over s smooth, then point 1 to 5 are almost satisfied. Why I say almost? Because it don't find really a peak 0, but an abelian scheme instead of peak 0, whose fibers are reduced fiber, the reduced component of the peak 0. But for my construction, I need it is an abelian scheme whose fibers are really the peak 0 and not the reduced component of the reduced part of the peak 0. So you can add an hypothesis, for example. But for the generic fiber, there is no problem since it is a characteristic 0. We can ask the dimension of the H2 of is 0, where S is a special point.
So are you assuming that the map, this is also projective or something?
Sorry?
When you, the map X to S, are you also assuming it's projective or something?
Maybe proper. Maybe proper. Yes. Yes, I think it's proper.
At least proper.
Yes, yes. Yes, thanks. And it is.
So it's not necessary to be projective?
I don't remember if we need to be projective, but probably because when it is projective, in general everything goes well. But honestly, I don't remember. But what is important for the moment is that we don't ask assumption on the dimension of x. For curves, more or less, everything is well known. So I think I don't have enough time to even start the proof of theorem 1 in the case of curves, so it's probably a good time to stop.
Question?
Yes, a small question. What do you mean by the superscript R?
And it's not R, it's tau. So here I mean
Tau.
it's tau. Means stands for torsion. Is in some sense because it is similar to the torsion part of the Nevon Severi.
Makes sense, but
okay, sorry.
So it's not. It's tau.
Tau.
Okay.
Actually, this is the divisible part.
Sorry.
It's not the torsion, but it's the divisible part.
Yeah, but if you construct the Nevon Severi group scheme, like
Imagine
peak quotient.
that you have the Jacobian. Intersection of n to the minus 1 is always the whole image.
Union.
Yeah, the union. N to the minus 1 on the Jacobian is the whole Jacobian.
Jacobian for Jacobian of smooth
This
curves.
is zero.
This is 0.
Zero.
Tau and fixed node are the same.
It's n to the minus 1. It's the pre-image of.
These are the line bundles whose some power of which lines are pick 0. That's the definition. L such that L times n is in pick 0 for some n.
I do not understand the notation. Is n not the multiplication by n?
Yes.
What is n to the minus 1? Is not the inverse map to this?
Inverse image.
The inverse image?
Yeah.
What is the image of the multiplication by n on pick 0?
As I said, those line bundles L such that L tensor n is in pick 0.
It's multiplication by n on the whole peak.
Yes. And the section of this is pick 0.
What intersection?
N on pick 0 is subjective.
Yes, that's right.
Therefore, n to the minus, therefore pick 0 is contained in in the pre-image of n.
No, that's true. Yeah. Pick 0 is
So
contained
therefore,
in
the
pick
union of all this is pick. I don't know. So this is not the torsion. This is the divisible part.
The union of all these
Divisible,
contains
divisible,
certainly
right?
peak 0.
Intersection of multiplication by n, image of multiplication by n would be divisible. Intersection of n pick 0 would be divisible. Union of n inverse pick 0.
My point was only why torsion, because pick 0 is contained in this, and pick 0 is not torsion.
Yeah, but it's a torsion mod pick 0. That's what he's saying. That Neron's very
Zero
tau.
becomes torsion.
I say torsion because it is
For me, it's just at the
torsion
beginning I
of the
thought that
nerve-
it's really
the
the
big
torsion,
nerve
but
cell.
finally it's not the torsion.
If you want, it's saturation of pick 0. That's one of the ways.
Is it reasonable to expect that theorem 2 holds for solvable torsors?
I think in some cases it can be true because the problem is that when we have extended the problem for extending solvable torsors is that before extending solvable torsor we have to be able to extend tower of commutative torsors. So once we have extended a commutative torsor, one should ask if on these torsor, the assumption 1 to 5 are satisfied. And there are probably cases where this is true, probably in characteristic 0 or even in the 0 p characteristic, with some further assumption, but I'm still studying it at the moment. For curves, for example, in the 0p characteristic, maybe this should be true. And then once we have extended a tower of torsors, suppose the first tower of torsors is itself a torsor, then we have a method to prove that the extended tower provides us a torsor extending the starting one.
It would be interesting to see what happens for a general G, because probably for a general G that's not true. But I don't know how
Probably
to
it's not true.
find the context of it.
But odd order after an extension is solvable.
Maybe just a remark, this is relevant, I think, to the specialization of fundamental groups, because if you take, for example, inequal characteristic 0p, if you start with GP group, then in general this doesn't have a good reduction. But if you show that it has a structure of a torsor somehow, this is an additional structure.
But with this extension theorem for curves,
No, the extension here, I proved it here for curves, but it holds for in every dimension. And this is in some sense a consequence of theorem 1, because we have an exact sequence of group schemes which commutes with base changes. So more or less we can say that the abelianized fundamental group scheme of x eta is isomorphic to the generic fiber of the abelianized fundamental group scheme of x. So in general we have this. And this will imply that every torsor, every morphism, so this is a morphism on this group, it's here because we have an endomorphism. And so by standard construction like the one I showed here, we can extend every torsor. So in general, which is the difference is that in general, the fundamental group scheme, the abelianized fundamental group scheme of x, if x is a curve, I can briefly write that like the n torsion x0 over xs. If x is a curve, it is no more true if x is not a curve, but here we have tau, and we cannot take every n because it's not flat in general, but you can take a multiple of n. For example, multiply n by the order of the Neuroseries tau, and you're right. So this commutes by base change, and you have this isomorphism. But if you need more details, I've almost finished the reprint.
Perhaps in the kernel of this exact sequence, you should also put tau.
Sorry. Sorry. Of course, thank you very much.